Okay, g'day students, welcome to our first lesson in topic 2. We're looking at graphs today. So we want you to do a bit of jargon busting today, particularly so we want to understand the terms of the meaning, understand the meanings of the terms graph, edge, vertex, loop, degree of vertex, subgraph, simple graph, complete graph, bipartite graph, directed graph, or a digraph, and an arc. We'll leave off weighted graph and network for another day. Okay, so once upon a time, a bunch of people over in Russia, I think it was, looked at this series of 7 bridges and wondered if there was a way to cross all of those 7 bridges without having to cross one more than once. And that's one of the first ways of thinking about graphs and network theory. Now, you're familiar with the Bundaberg bus situation. So what we have here, we also have a network here of buses that go throughout Bundaberg. And I just nicked that off the bus link thing this morning. You can see that there are various paths that the bus takes through the road network. So we can understand that a network can be a series of connected lines here. Currently we can see that it can be, for example, your circulatory system may have blood vessels going throughout your body, or you can see here in Brisbane the rail link. You could also think about the power or computer or social networking. In fact, the world is getting more and more connected, isn't it? So our first definition of the day is that a graph refers to a network diagram, which is a collection of one or more points. Now each point is called a vertex, and the line segments that connect them are called edges. So to continue with the jargon, so one vertex is a point on a graph. Sometimes we call that a node. Now isolated vertices are not connected by an edge to another vertex, so there's no line between the dots. The edge is that line that connects the two vertices. When that edge has a direction, as in a digraph, we're going to call them an arc. Now the degree of a vertex in a graph is the number of edges that connect with that vertex, and you're going to count the loops twice. There's no loops in this diagram. We'll look at that next slide. And the face is the faces of a planar graph are the regions bounded by the edges, including the outer infinitely large region. So I think this is one we just need to pay attention to. You can see here we've got 2 faces on this graph. We've got the inside region, which is face 1, and then the outside region is face 2. So we always count the outside region as a face. So have a look at the diagram on the right hand side. A loop here is that edge that connects a vertex to itself. So it's this thing here. Now a single loop will add a degree of 2 to a vertex. So you can see at this vertex here we have the loop, which is counted as 2, and then we have another edge and another edge. So this vertex here has a degree of 4. If I have a look at this vertex, it's got this edge and this edge, so it has a degree of 2. Now in a connected graph, each vertex is connected directly or indirectly to all other vertices and can be traced without lifting your pen off the page. So this is what we call a connected graph. This one down here is obviously not a connected graph. This line here is what we call a bridge. And a bridge is an edge in a connected graph that if removed, leaves the graph disconnected. So that edge that joins essentially 2 different graphs is called a bridge. So when you're trying to draw up graphs, it's always a good idea to start off with a pencil. Now it doesn't matter too much if yours looks different to your neighbours, because they will inevitably do a bit, as long as it fulfills the requirements. So let's have a look at drawing a connected planar graph. In this case it's got 4 vertices. Well, I'm just going to think of a square. 1, 2, 3, 4. Now it's got 8 edges, so they're the lines that go across, and then we've got to draw it so it fulfills this example. So 1, 2, 3, 4, and I've got to draw another, how many edges? Another 4 edges. So 5, 6, 7, 8, and I've got to determine the number of faces to make this an fulfill Euler's formula. I can tell straight away that I've got too many faces to do this, so what I'm going to do is I'm going to draw it across there so my lines do not cross. So let's see if this works now. What I'm going to do is count the number of vertices. Well, what do we say? We've got V equals 4. Now, number of faces, let's count them out. 1, 2, 3, 4, 5, 6. That's looking good to me. And what else we want to do? So, it says to count the number of faces, so I should have done the equation first, but we'll do that in a second. And the number of edges, we've got 4 vertices and 8 edges. So all we do now is just do the substitution. So, it says we should have 6 faces there. So just sub that into Euler's formula. So what do we say? V plus F minus E. V plus F minus E should equal 2. So we've got 4 plus 6 minus 8 to equal 2. And you can see that each vertex has 4 edges connected to it. So each vertex therefore has a degree of 4 as well. A subgraph contains parts or another graph, but may be missing some vertices or edges. So any edge remaining in a subgraph must join the same vertices as in the original graph. A simple graph contains parts but no loops or multiple edges. And a simple graph may be connected or disconnected. A complete graph is an interesting one here. So it's just a simple graph in which every vertex is joined to every other vertex by an edge. A complete graph with n number of vertices is denoted as k sub n, and Euler's formula can be rearranged to say what the number of edges is the number of vertices multiplied by the number of vertices minus 1, and then all of that over 2. An isomorphic graph, if I break this word down, iso just means the same and morphic means the shape. So we're really just saying we're drawing the same shape a slightly different way. So isomorphic graphs are equivalent, that is that they contain corresponding edges and vertices. And you can see that I've drawn graph 1 to graph 2 here. Graph 2 is a planar graph, so it's got nothing crossing over the other. So let's think about planar and non-planar graphs. So a planar graph is a graph that can be drawn on the plane. So a planar graph can always be drawn so that no 2 edges cross. So we're familiar with our picture of a cube here. Can we redraw a cube as a planar graph? Yeah, well, we can. And you can see that I've done that here just from an isomorphic projection, which you learnt back in grade 8 maths if I was the teacher. But that's a long time ago, so it doesn't hurt to have a look at it again. So let's have a look at our diagram. So down on the bottom left, we've got a planar graph here on this side here. So nothing is crossing over. So if the edges are crossing, then Euler's formula doesn't really work for it. But you can see that in this one this one is it's got crossing over. An isomorphic projection of it is what? We can redraw it as a planar graph, but this one we cannot draw as a planar graph because we still have edges crossing. So this one is a non-planar graph. So let's have a look at another go at Euler's formula. So this works for connected planar graphs. So we've got the vertices and the faces and the edges. So, and Euler's formula tells us that we've got the vertices plus the faces minus the number of edges should equal 2. So in here we have 17 vertices. So what are the vertices? They are the little orange dots here. So we've got 17 of them. How many faces do we have? Well, we've got the head, the body, and the outside of this ant. And let's have a look now at the number of edges. That's the number of lines. Now, be careful. This is not a loop. It would be a loop if if it didn't have different vertices in there. So that's 1, 2, 3, 4, 5, 6, 7, etc. In terms of edges. So does this fulfill the requirements of Euler's formula? Is that a connected planar graph? Do the number of vertices plus the faces minus the edges equal 2? Yes. So therefore this graph is connected and planar. So let's have a look at Euler's formula. Apparently meant to say Euler and not Euler. So let's look at our diagram here, and you can see I've scribbled over it already. So let's just count off the faces first of all. So we've got the outside region, which is face 1. And we've got this inside region, face 2, another inside region, face 3, and then face 4. So we have 4 faces. Let's now count the vertices. So the vertices are all those points. So, little 1, 2, 3, 4, 5, 6. So we have 6 vertices. And now let's count the edges. 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 edges. So what we now look at Euler's formula, it says the number of vertices plus the number of faces minus the number of edges should always equal 2. So we can just substitute that into the formula, and you can see, yes, that fits Euler's formula. Now a cycle is a closed path that does not repeat vertices except for the starting to ending. Now a tree in a network is a connected graph with no cycles. So a tree has no cycles, no loops. It only has one face, and it's the exterior face. The number of edges in a tree is just the number of vertices minus 1. We've got some bipartite graphs, and that's the graph with whose set of vertices can be split into 2 distinct groups in such a way that each edge of the graph joins a vertex in the group to a vertex in the second group. A diagraph, you can see here, has a direction. So it has a diagram comprising of points called the vertices, joined by directed lines. Now we're calling them arcs because we have a direction, and we can call directed graphs diagraphs. Now the arrow may indicate, for example, the flow of traffic on a one-way street, a predator-prey relationship. So an eagle might eat a snake, for example, which then eats something else. Or a competition, so competitor A beat competitor B in a competition. If we have a look at using Euler's formula for a complete graph, we're going to use the second formula here. So we've got a complete graph with 5 vertices. So it's essentially what a pentagon with all the corners joined together. So we want to determine the number of edges and the degree of each vertex. So we say, well, we've got how many vertices? We've got 5 vertices. So to determine the number of edges, we just substitute in the second relationship 5 for v, so 5 times 4 equals 20. 20 over 2 should equal 10. Let's draw that up. So as I said, it's like a pentagon, and it's got lines connecting each vertex. So those lines are called edges, and each vertex has 1, 2, 3 edges to it, so it has a degree of 4. We've done a lot of jargon today, and we've looked at Euler's formula briefly. Are you able to understand the terms graph, edge, vertex, loop, degree of a vertex, subgraph, simple graph, complete graph, bipartite graph, directed graph, or a digraph? We did briefly mention network, but we haven't talked about weighted graph yet. When you're done there, please work on exercise 7.1.